Hello everyone, welcome to Goscore Learning. So we are Goscore Learning. We are the fastest growing edtech in GCC. So our aim is to provide education for all. So as part of that, we have started a online series on YouTube. So today, my name is Rahul and I am from Department of Physics, Goscore Learning. So I am a postgraduate in physics from Mahatma Gandhi University, Kuwait Time, as well as a graduate in education. So today's class I am going to discuss you with grade 12 physics. Okay. So if you are looking to the syllabus of grade 12, we can see that for the first unit, in the first unit it contains two chapters, chapter 1 and chapter 2, and for unit 3 they contain one chapter, current electricity. So from that chapter, if you see, means you can see that out of 70 there will be 16 mark question will arise from that particular 3 chapters. Okay, from unit 3 and unit 4 there are 4 chapters. The chapter 4 moving charges and magnetism, and chapter 5 magnetism and matter, and from unit 4 it is chapter 6 electromagnetic induction, and chapter 7 alternating current. So there will be 17 marks question will be asked from that particular chapters, chapter 4, chapter 5 and chapter 6, chapter 7. So if you see, means there is no chapter wise weightage for this chapter. So only the question can be asked from either of these chapters. No chapter wise weightage will not be there. Only the mark is distributed among the 2 units. Okay. So in this class, in this session, I will be discussing with chapter 4 moving charges and magnetism. Okay. So in the first 2 chapters of grade 12 physics, we are dealing with electrostatics. So what is electrostatics? So if you see, means electrostatics means, what is the meaning of the term statics, which is stationary. So the electrostatics deals with stationary charge. So the 4th and 5th chapters deals with magnetostatics. So what is magnetostatics? Is that magnet at stationary? No, it is not that magnet at stationary, which means the moving charge creates current. Moving charge creates current. So magnetostatics, which is dealing with steady current, not only steady current, the steady current. So magnetostatics deals with steady current. So in the 4th and 5th chapters we are dealing with magnetostatics, which means we are dealing with steady current. Okay, so in that term magnetostatics, it is understood that the magnetism arises from current. That means moving charges. That's why the chapter name moving charges and magnetism. Okay, so if you see in this chapter, so there are particular topics in this chapter which to be covered: magnetic field, Easton's experiment, Biot-Savart law, magnetic field on the axis of a circular current loop, Ampere's circuital law, application of Ampere's circuital law, Lorentz force, force on the current carrying conductor in a magnetic field, force between 2 parallel currents, torque experienced by a current loop placed in a uniform magnetic field, as well as the last one, moving coil galvanometer and its conversion into a voltmeter and ammeter. So these are the topics which included in this chapter. So I will be discussing some of the first 4 topics in this chapter. Okay. So moving with magnetic field. So what is magnetic field? What is magnetic field? Any idea? So in the first chapter of grade 12 physics, you have learned about electric field. So what is electric field? What is electric field? Any idea? Do you remember that? Okay, so electric field means, so consider a electric charge, suppose an electrode. Okay, so the region around this electric charge in which its influence can be felt, that is what is called electric field. Same like, so consider a magnet. So here we have north and south poles of magnet. So we know that there will be magnetic field around this magnet, and what is that? It is the region around a magnet in which its influence can be felt. So we know that from north pole to south pole there are magnetic field lines. Yes or no? So there will be magnetic field lines. So It is arises from north pole of the magnet and ends in south pole. So magnetic field outside the magnet start from north pole and ends in south pole. So what will be the direction of magnetic field inside the magnet? So magnetic field always forms a closed loop. So we can say that simply the direction of magnetic field inside a magnet from south pole to north pole. But outside of the magnet, its direction from north to south. So did you remember what is the letter used to denote magnetic field? Do you think that it is M? For electric field, we use E. But what is for magnetic field? It is not M. The letter we use to denote magnetic field is B. Okay. So as like electric field, magnetic field is also a vector field. Okay, it's a vector field, and we can simply denote it by the letter B with a vector symbol. So magnetic field is a region around a magnet in which its influence can be felt, and it is denoted by the letter B. So if you remember that parallel plates, so if you remember the electric field lines, no two electric field lines cross each other. Why? If they cross each other, we know that since they are vector field, they will have two direction at a single point. At the point of intersection, they will have the two direction. So as like magnetic field, they will not cross each other. No two magnetic field lines cross each other, because if they do so, suppose these are two magnetic field lines. So if they cross each other, means at this point of intersection, the point of intersection, they will have to say two direction, which is not possible. So no two magnetic field lines cross each other. Okay, so that are the some preliminary idea about magnetic field. So we can move to the first topic in this chapter, which is Easted's experiment, and we write it as Oersted and read it as Easted. Okay, so hence Christian Easted have conducted an experiment approximately 200 years ago, and before that we are able to know about electricity and magnetism. But through his experiment, it is understood that for the science world, it is understood that electricity and magnetism are interrelated. So how he is experimented that thing? Let's see. So here I have considered a circuit. So there is no switch. Okay, so I can. Okay. So there is a switch. So this is a circuit in which a cell is connected, and we can see a magnetic needle. So magnetic needle, in simply it is a magnet which have light weight. Okay, so here we have one magnetic needle pointed on a stand. Okay, so when the circuit is switched on, through his experiment, it is understood that the magnetic needle has a deflection. It is deflected towards the conductor. So when he just reverse the direction of current, how can he reverse the direction of current? Any idea? Any idea regarding that? So how can he reverse the direction of current? So just reversing the polarity of battery. If you place the battery like this, we can change the direction of current. So for this circuit, the direction of current starts from positive and ends in negative. So this will be the direction of current. Okay, so when a current passes through this conductor, we can see a deflection for the magnetic needle. So it's only because there will be a force of interaction, right? There will be a force of interaction. So he came to the conclusion that when a current passes through a conductor, magnetic field is created. Whenever a current passes through a conductor, there will be magnetic field around it. So here we know that the magnetic needle itself is a magnet, so it has its own magnetic field, and when a current is passes through a coil or a conductor, there will be magnetic field, and these two magnetic field comes into interaction, and that interaction force made the needle deflected. Okay, so the needle deflected because there is a magnetic field created by the current carrying conductor. So it's the conclusion of his experiment is that, first conclusion is that a current carrying conductor creates a magnetic field around it. Okay, so I hope that is clear. So one more thing is that when he changes the direction of current, he can see a reverse in the direction of deflection of the needle. So whenever the direction of current reverses, as like if you have placed it So if you place a cell like this, which means reverses the direction of current, which means the reverse order, you can see a opposite deflection in the needle. That is because there is a change in direction of magnetic field when the current reverses. So the first conclusion is that a current carrying conductor creates a magnetic field, and second point, whenever the direction of current changes, there will be a change in the direction of magnetic field as well. So one more thing, whenever the intensity of current increases, which means if current increases from I to some more than I, then the intensity of deflection of needle also increases. So there are three conclusions for his experiment. First one is current carrying conductor creates a magnetic field. Whenever the direction of current changes, there will be a change in direction of magnetic field by the conductor. And third one, when the intensity of the current increases, there will be a change in, which means there will be increase in intensity of magnetic field. So these are some preliminary idea about Easted's experiment, even though it is not a vast area in our syllabus, it is simply mentioned in our syllabus. Okay, so the point you have to remember is the current carrying conductor creates a magnetic field, and the direction of magnetic field depends on the direction of current. So third point, the intensity of magnetic field increases with the intensity of current. Okay, so these are the points we have to remember about Easted's experiment. Okay, so through his experiment, it is understood that current carrying conductor creates a magnetic field. So only, but I will add one more point, only current creates magnetic field. Only a current can create a magnetic field. So how is possible for a magnetic needle or a bar magnet, how does it create magnetic field without current? Is that possible? Any idea? Do you have any idea how a bar magnet creates magnetic field? I said that only current can create magnetic field. So did you know how a bar magnet produces electric field? So we know that Earth has its own magnet, right, within the core. So there is any current within the Earth core which produces magnetic field? Any idea? So please go through that portion. This is I give to yours. You can find the answer by referring somewhere else. Okay. So only current can create magnetic field, and through Easted's experiment, it is understood that current and magnetism are interrelated. Is that okay? Can I move to the next portion? I hope it is okay. And if you have any doubt, just rewrite it. Okay. So we can move to the first main topic of this chapter, which is Biot-Savart law. Okay. So Biot-Savart law. So I think you will be able to remember about Coulomb's law in electrostatics. Same like we have Biot-Savart law in magnetostatics. I will after finishing this law, I will explain how the Coulomb's law and the Biot-Savart law are interrelated. Okay. So for explaining Biot-Savart law, just consider a current carrying conductor. Okay, current carrying conductor XY carries a current I. Okay, so consider a current carrying conductor XY carries a current I. So through Biot-Savart law, we are going to derive an expression for magnetic field created by a current element. Current element means a small length which having a current, a small length. We are usually denoted by the letter dl. Current element is a vector because it is a length along with the current. So current element means a small length carries a current. Okay. So through Biot-Savart law, we are going to explain about the magnetic field created by a current element, a small current element. Okay. So since it is a small current element, the magnetic field will be also small. Okay. So consider a current carrying conductor SY carries a current I in the upward direction. Okay. So I wish to mark the axis of the current carrying conductor is marked by the white dot lines. Okay. So imagine a small current element having a length dl. Okay, a small current element having length dl carries a current I. Okay, so we are going to derive an expression for, or we are going to state the expression for magnetic field due to this current element dl at a point P. Let P be a point which is situated at a distance, r from the middle of the current element. So r is a vector. Okay. R is a vector, dl is a vector. So we are going to derive, or we are going to state the expression for magnetic field at the point P due to the current element dl, which is at a distance r from the middle, okay, from the middle of the current element. So dl is a vector, r is a vector. So I state a small angle theta, which lies between the vector dl and r. So I will explain this once again. Consider a current carrying element xy, that is a current I. Consider a small current element dl, which is a vector. Consider a point P in which we are intended to measure the magnetic field strength on that point, and which is at a distance r from the middle of the current element, and the angle between the position vector for P and the current element dl is theta. Okay, so Biot-Savart law state that the magnetic field at a point P, which is dB, since it is a small magnetic field created by a small current element, there will be definitely a small magnetic field. So the magnetic field dB at the point P due to the current element is directly proportional to the intensity of current, or the current I. dB is proportional to the current I. So that's the first point. And the second point, dB is proportional to the length of the current element dl. And the third point, dB is proportional to sin theta, sine of the angle between the position vector r and the current element dl. So first 3 points, dB is proportional to y, dB is proportional to dl, and dB is proportional to sin theta. And fourth and last point, dB is proportional to this 1 by r square. R square means distance to the point P. So these are the 4 points. First point is dB is proportional to y. Second point, dB is proportional to dl, the length of the current element. And third point, dB is proportional to sin theta. And the final one, dB is inversely proportional to r square, or dB is proportional to 1 by r square. Okay, so how can we integrate it? So simply we can write it together. dB is proportional to I, then dl, and then sin theta divided by r square. Can I write it like this? dB is proportional, I state it together. So Biot-Savart says that the magnetic field due to a current carrying conductor and due to a current element dl is proportional to the current I, length of the current element dl, and sin theta, and inversely proportional to r square. So simply I dl sin theta by r square. So how can I? So we have the equation dB is proportional to I dl sin theta by r square. So to change proportionality symbol to equal to symbol, what we can do? So dB is equal to, what is dB? We should multiply it with a constant, right? So the constant here is mu 0 by 4 pi. I will explain it later. Okay, so the constant here is mu 0 divided by 4 pi. Okay, so mu 0 by 4 pi I dl sin theta by r square. Is that clear? So we have the Biot-Savart law, dB is equal to mu 0 by 4 pi I dl sin theta by r. So what is mu 0 by 4 pi? So here mu 0 means magnetic permeability of the medium. Here it is free. Mu 0 means it is the free space or vacuum. Okay, so magnetic permeability, you can see, if you remember Coulomb's law means there is a constant 1 by 4 pi epsilon 0, and this epsilon 0, what is epsilon 0 there? It is electric permittivity, and here the mu 0 means magnetic permeability. So there is a chance for you guys to interchange between magnetic permittivity or magnetic permeability. So how can we remember? So this is a Greek letter and pronounce it as mu, and here we have permeability, and don't read it as permeability, read it as permeability, and remind in your mind permeability, mu 0 permeability. So you can relate like that. It is electric permittivity. electric permittivity, and this is magnetic permeability. Mu 0 means permeability of free space. So what is permittivity and permeability? Any idea? So electric permittivity means it is a measure of how allows that particular medium for the electric field. It's a measure of how that particular medium allows electric field. Same like magnetic permeability means it's a measure of how that particular medium permits that magnetic field lines to pass through it. So this is magnetic permeability. Okay, so the value of mu 0 divided by 4 pi is equal to 10 to the power minus 7 Tesla meter per ampere. So 10 to the power minus 7 Tesla meter per ampere. Did you remember what is 1 by 4 pi epsilon 0? Anybody? Please put it in the comment box. Okay, so what is value of 1 by 4 pi epsilon 0? Okay, this is mu 0 by 4 pi is equal to 10 to the power minus 7 Tesla meter per ampere. So Tesla means the unit of magnetic field is Tesla. We see it later. Okay, so from this, what is mu 0? Any idea? Mu 0 equal to, simply we can multiply with 4 pi, right? So 4 pi into 10 to the power minus 7 again Tesla meter per ampere. You should remember both these values. Okay, so mu 0 by 4 pi is equal to 10 to the power minus 7 Tesla meter per ampere, or mu 0 is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. This may you should remember if you going for some solve some numericals. Okay, so mu 0 is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. I hope this is clear. So what is Biot-Savart law? Biot and Savart, they are the names of two scientists. Okay, so I'll say Biot-Savart law. Okay, so Biot-Savart law gives a measure of magnetic field due to a small current element, and dB is equal to mu 0 by 4 pi IDL sin theta by r square, and the mu 0 is known as magnetic permeability of free space. Is that okay? Is that okay? Okay, so we have the expression dB is equal to mu 0 by 4 pi I dl sin theta by r square. Okay, so I wish to write like dB is equal to mu 0 by 4 pi I dl into r sin theta by r cube. Okay, since we have multiplied with r in the numerator, so it should be r cube. So what's the purpose of this? Any idea? Okay, let's see. So for that I have a question. Is current is a vector? The current is a vector quantity. Yes sir, current has direction. It is directed from positive terminal of the battery to the negative terminal, so it has direction, so it is a vector. So wrong. Current is not a vector. For a vector, it should have both magnitude and direction, as well as it should follow the laws of vector addition. Is current follows laws of vector addition? Do you remember about laws of vector addition? You have learned in grade 11 physics. I think the chapter of motion in a plane. Laws of vector addition. Did you remember that? Any idea? Okay. Is current follows laws of vector addition? So what is laws of vector addition? Suppose consider a junction. Current follows I1 in this direction, and current follow some current I2 in this direction. Is the resultant of this current is midway between this? Resultant of vector I1 plus vector I2 is there any imaginary conductor in between I1 and I2? So this is laws of vector addition, right? If a force acting in this direction and another force acting in this direction, the resultant force will be between them, right? Resultant force. Is current follows this law of vector addition? No. So current is not a vector. Current is not a vector. It's a scalar quantity. So here dl means length and the current element, right? It have along with have the current. So it is a vector quantity. So I wish to treat it as idl as a vector quantity. Okay. So dl is a vector quantity now. Then so can I write it like mu 0 divided by 4 pi I into, so since dl is a vector, dl R is a vector R. So dlr, what is vector dl cross vector R? What is that? What is that? This dlr sin theta into n hat, right? The vector dl cross vector R is dlr sin theta into n hat. So same like n hat means a unit vector which shows the direction of vector product, right? So here we have vector dl into vector R sin theta. I wish to write it like dl cross R. Is that okay? So simply it is dl cross R divided by R cube. Is that okay? So what is our equation become? So vector db is equal to, in vector form we can write it like db is equal to mu 0 by 4 pi I into vector dl cross vector R divided by R cube. So in vector form we can write Biot-Savart law in this form. Okay, is that okay? Clear? Is that clear? Give me a thumbs up. Okay. Okay. Then, so before starting Biot-Savart law, I said that there is a connection for Coulomb's law. Do you remember Coulomb's law? What is Coulomb's law in electrostatics? Coulomb's law gives the force of attraction or repulsion between two charges, right? So what is the force of attraction between two charges Q1 and Q2? It is 1 by 4 pi epsilon 0 Q1 Q2 if the charges are Q1 and Q2, and divided by if the separation between them is R, then 1 by 4 pi epsilon 0 Q1 Q2 by R square, right? So the Coulomb's law you have also stated it as inverse square law, because there is a inverse square dependence, right? So it is also known as inverse square law. Coulomb's law is also a inverse square law. So what about this one? If the final expression, not the final one. So this one is also inverse square law, right? So both them are inverse square law. So that is one connection. And one more thing. So did you remember how you derived an expression for electric field? From the equation, force experienced by a charge Q moving in an electric field is given by F equal to QE. And from this equation, you derived E is equal to F by Q, and it leads to the equation for electric field in the first chapter. If you remember, just recollect it. Okay, so from this equation, Coulomb's law equation, we have derived an expression for electric field. Okay, electric field. Here we have magnetic field. So Coulomb's law gives electric field, an idea about electric field, and Biot-Savart law gives idea about magnetic field. So I think you got the connection now. So we should compare both Coulomb's law and Biot-Savart law. So here we have the equation dB is equal to mu 0 by 4 pi. Equation is there, you can read it. Okay. So both of them are, this magnetic field is long range field. Both of them are long range field. And what about Coulomb force? It is long range force. So here we have the comparison. Okay. So I stated it later that inverse square law, Coulomb's law and Biot-Savart law are inverse square law. So they are inverse square law. Then Biot-Savart law, the magnetic field is produced due to a vector source IDL, current element IDL. And here what about Coulomb's law? Is charge is a vector? No, charge is a scalar quantity. So it is produced by a scalar source charge. It is produced by a scalar source charge. And if you see in the Biot-Savart law, there is an angle dependence. There is an angle dependence in this equation, and there is no angle dependence for Coulomb's law. Okay, I hope this is clear, and if you have any doubt, just rewind it. Okay, so yes, we have the question here. So for magnetic field to be maximum due to a small element of current carrying a conductor at a point, the angle between the element and the line joining the element to the given point must be dash, and there are 4 options. Okay, so how to find the answer for this? Any idea? Okay, what is the question? Magnetic field due to is maximum, right? So what is the expression for magnetic field that we have learned? It is dB is equal to mu 0 by 4 pi I dl sin theta divided by r square, where theta is the angle between vector r and vector dl, right? Okay, fine. So it will be maximum. There is an angle dependence sin theta. When will sin theta maximum? What is the maximum value of sin theta? What is the maximum value of sin theta? What is the minimum value of sin theta? Okay, so sin theta maximum when theta equal to when will be sin theta maximum? When will be sin theta 1? Theta equal to 0 or 90? 0 or 90? It is theta should be 90 degree, no? Theta should be 90, then only magnetic field will be maximum. Okay, so if sin theta equal to 0, which means theta equal to 0, sin theta equal to 0 means theta equal to 0, sin 0 is 0, right? So sin theta 0 or theta 0, what will be magnetic field? If theta is equal to 0, dB is equal to, simply dB is equal to, if this is 0, we are multiplying that, so the resultant will be 0. And when theta equal to 90, sin theta equal to 1, right? This is the maximum value of sin theta. So magnetic field will be maximum if theta equal to 90 degree, right? Since there is a sin theta dependence for this equation. So what is the answer? It's not 0, it is 90 degree. Is that clear? I hope is that clear. So okay, so we have seen that for the expression for magnetic field, so there is a theta dependence, right? So what is the angle theta? It is the angle between DL and R. So theta equal to 0 implies dB equal to, what is dB? If theta equal to 0, what is dB? Since it is sin 0 is 0, dB will be 0. So when will theta become 0? Theta becomes 0 when R is along the axis. R is along the axis, which means this line is along the axis. So the P should be on the axis of the point, right? Theta equal to 0 or theta equal to 1. Theta sin 180 is also 0. Okay, so when P is on the axis of the current element, magnetic field will be 0. Magnetic field will be 0. So when we are considering a point P on the axis, this is the axis of the current element. So when P is considering at the axis, theta will be 0, so that magnetic field will be 0. So just above or below the conductor or in the axis of the current element, magnetic field will be 0. So when theta equal to 90 degree, magnetic field dB is maximum, right? That we have learnt. So it is maximum when theta equal to 90 degree. So when will be theta equal to 90 degree? So both the axis of the current element and the point P, the plane of the point P should be perpendicular. Okay, so magnetic field due to a current element will be maximum at a point which is passes through the plane of the point should be passes through the current element and which should be perpendicular. The plane of the the plane of the point P and the current element should be perpendicular. Then only a magnetic field will be maximum. So it may be asked in MCQs or case study questions. So please be noted that when theta equal to 0, dB is 0. When theta equal to 90, magnetic field will be maximum. So you should remember what is theta. Theta is the angle between current element and the vector joining the current element and the point P. Okay. So relation between mu 0, epsilon 0 and C. So what is C? Any idea? Okay, let's see later. Okay, so after end of this derivation we will see what is C. Okay, so we have 1 by 4 pi epsilon 0 is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square, and 4 pi mu 0 by 4 pi equal to 10 to the power 7 Tesla meter per ampere. So from this equation, what is 4 pi by epsilon 0? What is 4 pi epsilon 0 from this equation? Simply 1 by 9 into 10 to the power 9 Newton meter square per Coulomb square, right? So what is 4 pi by epsilon 0 into mu 0 by pi equal to, what is 4 pi by epsilon 0? What is 4 pi by epsilon 0? It is 1 by 9 into 10 to the power 9. And what is mu 0 by 4 pi? It is 10 to the power minus 7, right? Or simply 10 to the power minus 7 means 1 by 10 to the power 7. Is that okay? Okay. So 4 pi cancelled, and what we have is epsilon 0 into mu 0. So epsilon 0 mu 0 is equal to 9 into 10 to the power 9 into 10 to the power 7. So what is x raised to m into s raised to n? It is s raised to m plus n, right? So here we have s raised to m into s raised to n. So it is simply 9 into x raised to m plus n, which means 10 to the power 9 plus 7, which is 16, right? So I wish to write it like 1 by 9 is 3 square. Sir, why are writing like 9 is 3 square? We know that. Okay, let's see. Why I have write it like 9 is equal to 3 square. And what is x raised to m raised to n? It is x raised to m n, right? So 10 to the power 16 means 10 to the power 8 all raised to 2. 10 to the power 8 raised to 2. Is that okay? Why are you doing like this? What's the purpose? Let's see. What's the purpose? Okay. So 3 square into 10 to the power 8 all square. Okay, then 1 by, we can write it like 3 into 10 to the power 8 whole square. Is that okay? Is that okay? If that is okay, then what we have got is epsilon 0 into mu 0 is equal to 1 by 3 into 10 to the power 8 square. So what is there any resemblance regarding 3 into 10 to the power 8? Did you remember? We are actually deriving this c, right? What is this c? It's the speed of light in vacuum, velocity of light in vacuum. What is velocity of light in vacuum? Did you remember? What is velocity of light in vacuum? C is the letter used to denote velocity of light in vacuum. So what is that value? C is equal to 3 into 10 to the power 8 meter per second. 3 into 10 to the power 8 meter per, it is an approximate value. Okay, so it is about 3 lakh kilometer per second. 3 lakh kilometer per second. Okay, it is 3 into 10 to the power 8 meter per second. Anyway, so this is 3 into 10 to the power 8, right? So we can simply write it like 1 by c. Okay. Now we got the relation, right? What is mu 0 epsilon 0 is equal to 1 by c square, or c square is equal to 1 by epsilon 0 mu 0, 1 by epsilon 0 mu 0, or c is equal to 1 by, all good, but you can simply write it epsilon 0 mu 0. So this is the expression connecting c, mu 0 and epsilon 0. So even though it is not in our syllabus, it may be helpful for you to solve entrance level questions. It's not in the syllabus, but you should learn about this equation because it may be helpful for you to solve some numericals in entrance exam like NEET and JEE. Okay, as well as I can also write it like epsilon 0 means permittivity of free space, right? And mu 0 means permeability of free space. For a particular medium, we can simply write it like velocity of light in that medium. I wish to write it like V. Velocity of light in that medium is equal to 1 by electric permittivity of that medium into magnetic permeability of that medium. Okay, so this equation is also needed one. Not for your board exam, but in the entrance exam, it may be helpful for you. Okay, so next important derivation is here, magnetic field on the axis of a circular current loop. Sir, you are stated right, circular current loop, but it is a elliptical in shape. What's happened? It's ellipse, right? But we have circular current loop. Wait, why don't you draw a circular loop? Okay, so I have a circular loop here. Okay, it's not circular now. Okay, it's become circular now. Okay, so this is our circular loop. So what's the heading? Magnetic field on the axis of a circular current loop. So what is axis of this circular current loop? Any idea? A line passes through this point. This is the axis. Now, what's the axis of this circular current loop? It's a point which passes through the center. And which is perpendicular to the plane of the loop. Okay, so for this circular current loop, this line, if my hand is the axis, this will be the axis of the circular current loop. Okay, so here, for make it simplifying, So I wish to place the loop which is the plane of the loop. This is the plane of the loop, right? I place the loop which is perpendicular to the plane of the board. That is why I have drawn it like this. Okay, I hope is that clear. Okay, any doubt? So I will repeat once again. This is our current loop, and instead placing it right like this, I wish to place it like this. Then only our derivation will be possible. Okay, so that is why instead of circular loop, I draw a somehow elliptical in shape. Okay, is that okay? So this will be the axis. And one more thing, the half portion, the semicircular portion of this loop is behind the board. Oh, but we are able to see the full portion, right? No problem. But for demonstrating it easily, I am stated the full portion in the board. But you just imagine like that, the current loop, the half portion is behind the board and half of the portion is inside the loop. Okay, for here, if the radius of the loop is given by r, the radius of the current loop is r, and this is the axis of the loop, and this loop is carrying a current I, and imagine it like this part is in front of the board and this side is behind the board. Okay, so there will be a current I which is passing through the loop. Okay, so I wish to find magnetic field, yes, at a point P. This is our point P. Okay, so this is our point P. So we are going to derive an expression for magnetic field on the axis of the current loop, and for that I have considered a point P which is at a distance x from the center of the current loop. So r is the radius and x is the distance to the point P which is located at the axis of the circular current loop. Okay, okay. So for that, what's our expression for magnetic field? Remember Biot-Savart law. What is Biot-Savart law? dB is equal to mu 0 by 4 pi I dl sin theta divided by r square, or equal to, in vector form I can write it like this, mu 0 by 4 pi I into dl cross r divided by r cube, right? dl cross r divided by r cube. Okay, so I am considering a small current element dl, vector dl. Okay, at the top portion of the current loop. So this is dl, and for here the dl having a current. So this, since this side is coming in front of the board, so the current dl is coming towards you. If you are seeing the direction of vector dl which is tangential, since this is a circle, the direction of dl is just tangential to the circle, and it is coming towards you, right? It is coming towards you, yes or no? So here the current is coming towards you. This dl, direction of dl is coming towards you. Okay, so I need the distance to the point P. So from this current element, I wish to draw a line to the point P, and which is r, position vector r. Okay, so r. So from that current element dl, a position vector have been drawn to the point P, and that is r. So since dl is towards you, and what about the direction of r, which is lying on this plane, on the plane of the board, right? dl is towards you and r is inside the board. Okay, so what is the direction of magnetic field? What is the direction of magnetic field? dB. Since this is due to the vector source dl cross r, the magnetic field will have the direction of dl cross r. So we have seen in the vector product rule, it is seen that the direction of vector product will be perpendicular to both the vectors dl and r. The direction of magnetic field should be perpendicular to dl and r, right? Yes or no? The magnetic field, direction of magnetic field should be perpendicular to dl and r, because dl cross r is there in the expression for dB. So direction of magnetic field should be perpendicular to dl and r. So dl is coming towards you, right? dl is coming towards you, dl is coming towards you, and r is within the plane. So what will be the direction, what will be the direction of magnetic field at this point P? Any idea? Any idea about that? Yes, any idea? So dl is coming, current element is coming towards you, and r is lying in the plane. So there are two possibilities. It should be perpendicular to dl and r. So every lane within the plane will be perpendicular to a point vector which is towards you, right? So every point within the board will be perpendicular to that. So dl is towards you and r within the plane, and the direction of magnetic field should be perpendicular to r and should be perpendicular to dl. So I have the direction like this. So there are two possibilities. Either the angle between dl and r should be like this, should be 90 degree, and there are two possibilities. This will be also 90, right? So there are two possibilities, and among this, what will be the right answer, right direction for magnetic field? Any idea? So to find the direction of vector product, we have right hand screw rule. Do you remember right hand screw rule? Two vectors a b, vector a and vector b. Okay, so the angle between them is theta. Angle between them is theta. To find the direction of vector a cross vector b, we should use the right hand screw rule. Do you remember what is right hand screw rule? Do you remember that? What is right hand screw rule? Okay, so take a right hand screw, and since it is a cross b, turn the screw from a to b. Since it is a cross b, turn the screw from a to b. So while you turn, the direction of advancement of the screw will give you the direction of vector product a cross b. So from a to b, I can turn the screw in this direction, right? In this direction. You should turn the screw in through the acute angle. This is also from a to b, right? But this is larger than 90, and you should turn the screw through the acute angle. That is a law for finding the direction of vector product. So from a to b, turn the screw in from a to b, then the direction of advancement of screw will gives you the direction of vector product. So if you apply the right hand screw rule here, you will be able to find that the direction of magnetic field along one, this one will be the right direction for magnetic field due to this current carrying element dl. Okay, and I wish to name the point as q. Okay, so this is the direction of magnetic field and which is along q. Okay, so you can note it there. So the direction of magnetic field dB, whose magnitude is mu 0 by 4 pi I dl sin theta divided by r square along pq, right? Along pq. So this is the direction of dB. So here there is an angle dependent sin theta, right? So what is theta? Theta is the angle between r and dl. So r and dl is here. So here we have dl, which is point towards you, and here we have r. So what is the angle between dl and r? Any idea? What's the angle between dl and r? dl is point towards you and r is lying in the plane. So what's the angle between them? It is 90 degree. Since dl is towards you and r is lying in the plane, so a point which is towards you and a lane which is in the plane will have angle 90 degree. Yes or no? So theta here is, what is theta here? Theta will be 90 degree. Theta here is 90 degree. Okay, so what will be now? dB is equal to mu 0 by 4 pi I dl sin 90 by r square. Okay, so along pq. So what is sin? What is sin 90? Sin 90 is equal to 1. So it will be equal to mu 0 okay, so it will be equal to mu 0 by 4 pi I dl by r square, r square. Okay, along PQ. Okay, so we can move back to the diagram. So here I have considered a current element dl above top point of the circular loop. Consider a diametrically opposite current element dl over here. So since it is a circular loop, here the direction of dl, which is towards not towards you, into the plane, right? Since this is a circular loop, here the direction of current is into the plane, right? So which is having an opposite direction. So for this one, at a point P, there will be a magnetic field due to the diametrically opposite current element dl, and this distance, what will be this distance? This will be also r, or no? If this is r, this will be also r. So what is the direction of magnetic field here? If you are applying the same concept over here, it should be like that. Okay, which is opposite to dB. Is that okay? No, it is not okay, because the angle between r and the direction of magnetic field should be 90 degree, which is not, which will be possible if and only if have a direction like this. Okay, so this will be the direction of magnetic field dB, and I wish to call it as q dash. Okay, so this angle will be, okay, so since the angle between dl and r is 90 degree, again it will be, what's the magnitude of that current for magnetic field? So again dB will be equal to, dB equal to, due to magnetic field due to the diametrically opposite point, dB is equal to mu 0 divided by 4 pi I dl by r square. Since theta is 90 degree here, sin theta will be 1, so simply write it as I dl divided by r square along p q dash. Is that okay? So we have 2 dB, this PQ, one along PQ and one along PQ dash. Okay, so their magnitude are equal and direction is just somehow opposite. Okay, so what will be the resultant vector direction? What will be the direction of resultant magnetic field? What will be the direction of resultant magnetic field? Any idea? So if two forces are acting, force 1, force 2, what will be the resultant vector? It will be, if the magnitude are equal, it will be the resultant will be midway between them, right? So we can simply say that resultant magnetic field will be along the axis. Yes or no? Along the axis. So by simply we can say it like that, but to make it in physics, we can go for some mathematics also. Okay, some geometrical identity should be applied, and then we can give the direction of resultant magnetic field is along the axis. Is that okay? Okay, so for that, if this angle is phi, what about this one? This will be also phi, right? This will be also phi. Then I wish to split the magnetic field dB into its rectangular components. Is that okay? I am going to split the magnetic field dB into its rectangular component in such a way that I need the components. One is perpendicular to x and the other should be along the axis, right? So I am going to split the magnetic field dB along PQ, and I wish to split one component is perpendicular to x, which means perpendicular to the axis, and one is along the axis. Okay, so any about what will be this angle? What will be this angle? Any idea? We know that the angle between this axis and this component is 90 degree, since it is perpendicular, right? So this will be 90 degree, and if this is phi, this will be 90 minus phi, right? 90 minus 5. This angle will be, the angle between R and the component will be 90 minus 5. Is that okay? This will be 90 minus 5. Then we know that angle between R and DB is 90 degree. Since this is vector product, right? This is vector product of DL and R, and the angle between R and DB should be 90 degree. So this is 90 minus 5. The total angle is 90. Then it should be, what will be on? It should be 5. Is that okay? Same like splitting this DB into its rectangular component. What will be this angle? Again it is 5. Is that okay? So don't worry about this geometrical identities. Just you can simply write it like this is 5. That's okay. No problem. Okay. So this is 5. Then so this component is near to 5, right? So this will be the cos component. So this is DB cos 5, and what will be this one? This one will be, if this is cos 5, then this component will be DB sin 5, because this component is near to the angle, right? So this will be cos component and this will be sin component. Same like this will be DB near to 5, right? Is cos 5, DB cos 5, and this will be, this will be again DB sin 5. So since the magnitude of DB are equal, DB cos 5 and DB cos 5 are equal and opposite, and they will be cancel each other. So only the remaining thing is DB sin 5 and DB sin 5. So as I said, the vectors, the resultant vector will be midway between them. We got the resultant of DB is along the axis. Is that okay? Is that okay? Yes. Now we can move to that. So in this figure, it is understood that the direction of magnetic field or the resultant magnetic field is along the axis. So it is only due to the sine component. Okay. So we have the total magnetic field is only due to the sine component. So for every current element within the circular loop, all the cos component will be cancel each other, and the resultant magnetic field is only due to the sine component which is along the axis. So what will be the resultant magnetic field? I wish to write like B is equal to which is due to the sine component. What is the sine component? DB sin phi, right? We should integrate it. So the total magnetic field will be equal to integral of dB sin phi. Okay, so what is dB? What is dB? Integral. dB we have mu 0 divided by 4 pi I dl by r square into sin phi. Ideal r square by sin phi. So from this equation, what is sin phi? Consider this triangle. Okay. So what is sin phi? Sin phi from this equation, what is sin phi? Sin phi means opposite side by adjacent side, right? So what is the opposite side? It is opposite side by hypotenuse. What is the opposite side here? It is r. What is the hypotenuse? This is small r, right? So sin phi simply r by r. Is that okay? Is that okay? Then we can move to the. So what we got is B is equal to integral mu 0 divided by 4 pi I dl by r square. What is sin phi? It is r by r, right? R by r. Okay. So simply mu 0 by 4 pi I dl r divided by r cube. So mu 0 is a constant, 4 pi is a constant, I is a constant, r is a constant, and r cube is also constant. So the varying thing is only dl. Varying thing is only dl. So simply it is mu 0 divided by 4 pi I r divided by r cube into integral dl. So we can move back to the diagram. So this is dl. What is integral dl? Integral dl means the entire length of the circular current loop. If the radius is r, what will be the total length? What will be the total length? Total length What will be the total length of the circular current loop if the radius is r? If the radius is r, the total length means the circumference of the current loop, right? If the radius is r, what is the circumference? It is 2 pi r, which is 2 pi r. Okay, so integral dl means 2 pi r. Is that okay? So mu 0 by 4 pi I into r into divided by r cube into 2 pi r. So 2 pi and 4 pi we cancel and 2 will be remaining. So which is equal to mu 0 divided by 2 into r cube into I r square. Okay, so we can again move back to the diagram. Okay, here what is r? What is r? Here r means the hypotenuse of the right angle triangle which having r and x axis side, right? So r will be equal to, hypotenuse means adjacent side square means, oh sorry, base square means perpendicular square, which means r square plus square root, which means all raised to 1 by 2. So this is the hypotenuse, so it will be equal to r square plus s square all root of r square plus s square, or simply I can write it like r square plus s square all raised to 1 by 2. So what is r cube? What is r cube? What is r cube? Just cube it, which is equal to r square plus x square all raised to into 3 means 3 by 2. Is that okay? So move back. Okay, here we have r cube, right? So which is equal to mu 0 divided by 2 into I r square divided by r square plus x square all raised to 3 by 2. I read it like. So what we have got is b is equal to mu 0 divided by 2 into I r square divided by r square plus x square all raised to 3 by 2. So this is the expression for magnetic field due to a circular current loop by the application of Biot-Savart law. Okay, so if there are n turns in the circular current loop, our equation will be B is equal to mu 0, n turns means n times, the sign will be increased to n times. So mu 0 n I r square pi 2 into r square plus x square all raised to 3 by 2. Is that okay? So this is the expression for magnetic field on the axis of a circular current loop. Okay, so if what is the magnitude of magnetic field at the center of the circular current loop? Center is also point in the axis, right? So center is also an axis. So here we have the diagram. Okay, so if this P is considered at the center, what will be 0? Is R is 0? No, radius will be the right. R is not equal to 0. What will be 0? Is this R is 0? No, only X becomes 0, right? Since P is into the center, X will be 0. So if at the center, what will be 0? So at the center, X equal to 0. So if you are applying X equal to 0 here, B is equal to at center, okay, at center implies B is equal to mu 0 into n into I into r square divided by 2 into r square plus x square, which means r square plus 0, r square plus 0, simply r square all raised to 3 by 2, all raised to 3 by 2. So x raised to m raised to n and s raised to mn, so 2 will be cancelled. So what we get is B is equal to mu 0 divided by mu 0 into n I r square divided by r cube. This again is equal to B is equal to and r cube R square cancel. What we get is mu 0 Ni divided by 2R. So this is the expression for magnetic field at the center of the circular current loop. Okay, so I think the topics are clear. If you have any doubt, just rewind the video. I think my words are clear. So just rewind the video if you have any doubts. So we can see up with another topic in the coming class. Okay, thank you for watching. Happy learning.